All right, taking a look at a video this time dealing with indirect proof, what it is, what it's good for, the steps that you need to follow, and then we're going to take a look at two little quick examples. Like anything else that has anything to do with proof, this is not a canned process where you can simply sit there and say, I know how to do this, follow these steps. There are steps to follow, but then the proving process can go in all kinds of different directions. So you need to be aware that this is a thinking process that you're being asked to go through here. So here we go. Let's first of all tell you what it is. Indirect proof is also called, oops, wrong pen there. Indirect proof is also called proof by contradiction. And what it does is it eliminates the other possibilities of the things that might be. So let me give you an example. So let's say I'm looking for my kids. We're playing hide and go seek. We're playing hide and go seek in my house. There are 4 rooms to hide in. Direct proof would be something like hearing giggling from somewhere, and therefore I have something that allows me to deduce to go straight there. That's direct proof. Just simply taking the information of what's going on, the rules I'm playing by, and I go directly to what it is that I'm after. But let's say I can't hear anything. Let's say I don't know what's going on. So another way to prove the room that the child would have to be in is by saying, well, they're not in this room, they're not in this room, they're not in this room, and therefore they have to be in that room. Without even having gone in there, I know that they have to be in that room. That's what proof by contradiction does. What it does is it eliminates all the other possibilities and leaves open the one that it is that I'm after. Because sometimes going directly there is not an easy thing to do. Sometimes there's a reason, particularly when it's greater than and less than. Anytime it's an inequality type situation, going directly sometimes is a pain. There are ways to go there directly when things are not equal, but at the same time, it's really helpful in a situation. And by the way, it can be helpful in pretty much any situation, even if things are equal or unequal or whatever the case happens to be. So just be aware that this is just a different way to do it. It's another format. You've got you've got 2-column proof, paragraph proof, and flowchart proof. Those are all forms of direct proof. Indirect proof is just simply a different way of going about the same thing. So rather than going directly to the source of what it is that I'm after, I'm eliminating all the other possibilities, and then I should end up with what it is that I'm seeking. All right. So how do you go about this? Steps to follow, and they have to be followed, have to be done in this particular way, is you have to assume the prove, or the then, is false. Right? What do you mean is exactly the opposite of what it is that I'm actually trying to prove. I'm assuming that's not the case. Right? So that would be, I'm assuming this is the one I'm trying to prove. In a direct proof, I'd be going after that. What I'm going to assume is, well, it's got to be one of those 3. And what I do is I systematically eliminate all the other possibilities, and therefore it has to be that one. So we assume the proof is false. You use the information to get a contradiction with the given. Meaning the information that you know has to be true. I'm trying to get myself to the place where I know that's not true. And then you point it out and finish. Right? So let's take a look at 2 examples of that situation. I'm going to assume the proof is false. I'm going to use the information I have to show that that cannot be, because the if part of the given conditions have to be true, no matter what you're doing. So then I'm going to point that out, that contradiction, and then finish. This proof will finish like any other proof, and that is it has to finish with what it is that you're trying to prove. All right, so here what we've got going here is we're assuming angles 1 and 5 are not equal. They're going to prove that the lines are not parallel. All right, so I'm going to do proof by contradiction. Use a paragraph form this time. So I'm going to say assume, and I'll go ahead and throw names on here. Let's call it A and B. So assume A is parallel to B. If A is parallel to B, then angle 1 has to be congruent to angle 5. because corresponding angles with parallel lines are congruent. This contradicts the given that angle 1 is not congruent to angle 5. I know it's the measures, but I couldn't type that very well, so I went this route. So my assumption is false, and the lines are therefore not parallel. Right? Simple enough. That's a proof by contradiction. I followed my 3 steps. I assumed what it was that I was trying to prove the opposite. I wanted to prove they're not parallel, so I assume they are parallel. Then I take that information, that thing that I've assumed there, and start following the logical consequences. The lines are parallel. Angles 1 and 5 are in a corresponding position, or therefore have to be congruent. If they have to be congruent, then that contradicts my given, which is that they are not. So then I pointed out my assumption is false, and therefore what I'm trying to prove is now proven. So what I did here is you had an option. They're parallel or they're not parallel. I showed that being parallel is impossible, therefore being not parallel is the correct conclusion. All right, second example. Assume the measure of angle 1 is bigger than the measure of angle 4, and the measure of angle 2 is smaller than the measure of angle 3. So I'm going to assume that the measure of angle 2 is greater than or equal to the measure of angle 3. And that's the reason I chose this particular example. Because the opposite of greater than is not less than, it's greater than or equal to. There are 3 possibilities for 2 numbers. If you have a number and another number, those 2 numbers, either the first is smaller, the first is the same, or the first is bigger. In this case, I'm trying to prove it is less than, so I have to assume the opposite or assume all the other cases. So if I'm after less than, that means I have to choose these 2, which is going to be greater than or equal to. So I'm going to assume the measure of angle 2 is greater than the measure of angle 3, greater than or equal to the measure of angle 3. Now I actually have 2 things I have to do here. I have to prove the greater than part, and I have to prove the equal to part. And I have to do them both. And yes, this makes this one a little bit longer than the way I would normally go about it, but it does help me show you that this type of idea takes 3 cases, and I've got 2 things to deal with. If the measure of angle 2 is equal to the measure of angle 3, then the measure of angle 1 is equal to the measure of angle 4 because the linear pairs add up to 180 degrees. So the other part must be equal. This contradicts my given. So that cannot be. If the measure of angle 2 is greater than the measure of angle 3, then the supplementary linear pairs say that the measure of angle 1 has to be smaller than the measure of angle 4. If 2 is bigger than 3, that means it takes up more space in the linear pair than 3 does. So there's less left over for 1 than there is for 4, so 1 has to be smaller than 4. And this also contradicts the given. So that is false, and my assumption is wrong, and the measure of angle 2 is smaller than the measure of angle 3. Game over. All right? That's not an easy process. A lot of students really end up loving this way of proving things. They feel like it's quicker and easier and makes more sense to them. You can choose whichever way you want. Obviously, on this particular lesson, you've got to do these things, and you may be asked to do something in an indirect manner, but down the road in your course, maybe you choose one or the other whenever you think they're easier. This is a good one to learn how to master if you can get the logic down in your head. All right? So that's indirect proof. Until next time, see ya!